Welcome to this coding problem walkthrough. In this session, we'll be exploring problem number 252, meeting rooms, where we'll analyze how to determine if meetings can be scheduled without conflicts. Stick around as we break it down step by step. In this problem, we are tasked with determining whether a person can attend all scheduled meetings based on their time intervals. Each meeting is represented as a pair, start-end, where start is the starting time and end is the ending time of that meeting. To attend all meetings, there must be no overlap between any two meetings. Overlap occurs when one meeting's time range intersects with another, meaning a person would have to be in two places at once. The input format requires an array of such intervals, and the output is a Boolean value, true if all meetings can be attended without overlap, and false otherwise. Let's explore some examples to better understand this scenario. Consider the first example, where the input is 0, 30, 5, 10, 15, 20. Here, the output is false. The reason is that two meetings overlap, 0, 30, and 5, 10, both include the time range from 5 to 10. Because of this overlap, it's impossible for a single person to attend all of these meetings, so the function returns false. Now, let's look at another example. In the second example, the input is 7, 10, 2, 4. This time, the output is true. There are no overlaps between these two meetings. The first meeting, 7, 10, starts and ends completely after the second meeting, 2, 4, has finished. Since there's no conflict in timing, a person can attend both meetings, meaning the result is true. Let's explore one more example to solidify this understanding. In the third example, the input is 1, 5, 5, 10, 10, 15, and the output here is also true. While the meetings are back-to-back, they do not overlap. The first meeting, 1, 5, ends exactly when the second meeting, 5, 10, begins. Similarly, the second meeting ends exactly when the third meeting, 10, 15, starts. Since there is no overlap between any meetings, a person can attend all of them, and the result is true. Now, let's consider some important constraints and edge cases. The constraints for this problem specify that the number of intervals can go up to 10⁻⁴, and the start and end times of each meeting can range from 0 to 10⁻⁶. Additionally, the intervals are not guaranteed to be sorted, so the solution must handle unsorted input. Edge cases to consider include scenarios like an empty input, where the result would be true because there are no meetings, or a single meeting, which also results in true since there's nothing to overlap with. Back-to-back meetings, like 1, 5, and 5, 10, should also return true as they don't technically overlap. Lastly, the solution needs to efficiently handle large intervals or inputs within these constraints to ensure optimal performance. To solve this problem, let's start by considering the brute force approach. The intuition behind this method is to check every pair of meeting intervals to see if they overlap. This involves iterating over the list of intervals and, for each interval, comparing it against all other intervals. If two intervals overlap, it means the person cannot attend all meetings. The steps are straightforward. First, loop through the intervals array. For each interval, you check whether its start and end times overlap with any other interval using the conditions provided. If any overlap is found, we return false, indicating not all meetings can be attended. Otherwise, if no overlaps exist, we return true. The trade-off here is that while this approach is simple and easy to implement, it is computationally inefficient with a time complexity of n², due to the nested iterations required. This makes it impractical for larger datasets, especially when the number of intervals grows significantly, even though it requires no extra space beyond the input array. To improve the efficiency of our solution, we use an optimized approach that leverages sorting. The intuition here is that by sorting the intervals by their start times, any overlapping intervals will appear next to each other. This eliminates the need to compare every pair of intervals and allows us to focus only on adjacent ones. Here's how it works. First, we sort the intervals array based on their start times. Then, we iterate through the sorted intervals and check if the end time of the current interval is greater than the start time of the next interval, which would indicate an overlap. If such an overlap is found, we return false. If no overlaps are detected after the iteration, we return true. This approach is much faster, as the sorting step takes O, n log n, and the subsequent single iteration takes O, n, resulting in an overall time complexity of O(n log n). While sorting introduces some overhead, it is a worthwhile trade-off for the significant reduction in runtime compared to the brute force approach. Ultimately, we chose the optimized approach using sorting as the best strategy for this problem. By sorting the intervals first, we achieve a significant improvement in time complexity, reducing it from O(n squared to O(n log n). This makes the solution much more efficient for handling large datasets. Sorting ensures that only adjacent intervals need to be checked for overlaps, which simplifies the implementation and minimizes unnecessary comparisons. The key advantages of this approach include its ability to handle larger input sizes effectively and its straightforward implementation. While the brute force method is simpler conceptually, its quadratic runtime makes it impractical for larger inputs. The optimized approach does involve a pre-processing step of sorting, but this is justified by the substantial performance gains. Additionally, this method assumes that sorting the intervals does not disrupt any requirements of the input structure, which is typically the case for this problem. Overall, the optimized approach strikes a balance between simplicity and efficiency, making it the preferred solution for this scenario. The problem asks us to determine if a person can attend all meetings given an array of meeting intervals, where each interval is represented by a start and end time. The main challenge here is identifying if any intervals overlap, as overlapping meetings would make it impossible for a person to attend both. To begin, we outline the brute force approach. The intuition behind this is straightforward: we compare every pair of intervals to check if they overlap. If any overlap is found, we return false, otherwise, we return true. Specifically, for two intervals, they overlap if the start of one interval is less than the end of the other, and vice versa. This approach involves iterating through the intervals array twice, resulting in a time complexity of O(n squared, where n is the number of intervals. While simple, this method is computationally expensive for large inputs, prompting us to explore more efficient solutions next. To optimize the solution, we can use a sorting-based approach. The intuition here is that by sorting the intervals by their start times, we can limit our overlap checks to consecutive intervals, significantly reducing the number of comparisons. First, we sort the intervals array, ensuring that all intervals are arranged in chronological order. Then, we iterate through the sorted list and check each interval's end time against the start time of the next interval. If the end time of one interval is greater than the start time of the next, an overlap exists, and we return false. If no overlaps are found after checking all consecutive intervals, we return true. This approach has a time complexity of O(n log n, for sorting in O(n), for the single iteration, making it much more efficient than the brute force method. Sorting plays a crucial role in this optimized approach, as it guarantees that all intervals are arranged in order of their start times. This ensures that any potential overlaps are limited to adjacent intervals, eliminating the need to compare non-consecutive intervals. It's also important to consider a few edge cases. If the intervals array is empty, we can immediately return true since there are no meetings to attend. Similarly, if there is only one interval, there is no possibility of overlap, so we can also return true. For cases with overlapping intervals, such as 1, 5, and 4, 6, sorting ensures these intervals are adjacent in the list, making it straightforward to detect the overlap. In terms of data structures, the input is stored as an array of intervals, which is then transformed into a sorted list. A single loop is used to efficiently check for overlaps in the sorted array. Let's walk through some examples to see the algorithm in action. For the input intervals 0, 30, 5, 10, 15, 20, the first step is to sort them, resulting in 0, 30, 5, 10, 15, 20. Next, we compare consecutive intervals. Comparing 0, 30 with 5, 10, we see that 30 is greater than 5, indicating an overlap, and we return false. For another input, 7, 10, 2, 4, sorting gives 2, 4, 7, 10. Comparing 2, 4 with 7, 10, we find that 4 is less than or equal to 7, so there's no overlap. Since there are no more intervals to check, we return true. These examples highlight how sorting simplifies overlap detection. Key operations include sorting to establish chronological order and a single pass through the intervals to check for overlaps. Edge cases, such as an empty list or a single interval, are straightforward, no overlaps are possible, so the result is automatically true. This completes the detailed breakdown of the algorithm. The solution determines if a person can attend all given meetings without any overlapping conflicts. Here's the step-by-step breakdown of the implementation. 1. Sorting the intervals. The input intervals list is sorted based on the start times of the meetings. This ensures that meetings are in chronological order, making it easier to check for overlaps. 2. Iterating through intervals. After sorting, the algorithm iterates through the intervals starting from the second meeting, index 1. The goal is to compare each meeting's start time with the previous meeting's end time. 3. Checking for overlaps. During iteration, if the start time of the current interval is less than the end time of the previous interval, it indicates a conflict, overlap. In this case, the function immediately returns false. For returning true, if no overlaps are detected throughout the iteration, the function returns true, indicating that all meetings can be attended. This implementation has a time complexity of n log n, due to the sorting step, where n is the number of intervals. The subsequent iteration through the intervals is n, making the solution efficient for practical usage. This is the Java implementation of LeetCode problem number 252, meeting rooms. It mirrors the logic of the provided Python solution. The intervals are sorted by their start times using arrays.sort with a lambda comparator. We then iterate through the intervals to check for overlaps by comparing the start time of the current meeting with the end time of the previous one. Java requires explicit handling of type declarations, and the 2D intervals array is represented as int. Unlike Python's dynamic lists, Java uses fixed arrays and utility methods like arrays.sort for sorting. The method returns true if no overlaps are found, otherwise false. The goal of this problem is to determine if a person can attend all scheduled meetings, given a list of meeting time intervals. Each interval is represented as a pair of numbers, the start time and end time. Two meetings are considered overlapping if one starts before the other ends. To solve this, the intervals are first sorted by their start times. This ensures that we can check for overlaps simply by comparing consecutive intervals. If any overlap is detected, the function returns false, indicating that the person cannot attend all meetings. Otherwise, it returns true. For example, consider the input intervals 0, 30, 35, 50, 60, 70. After sorting, we find that the intervals are already in order. Checking for overlaps, we compare the start time of the second meeting, 35, with the end time of the first meeting, 30. Since 35 is greater than or equal to 30, there is no overlap between these two intervals. Next, we check the third interval. Comparing its start time, 60, with the end time of the second interval, 50, we see that 60 is greater than or equal to 50, so there is no overlap here either. Since no overlaps are found after checking all consecutive intervals, we conclude that the person can attend all meetings, and the function returns true. Now, let's look at a different example with overlapping intervals 5, 10, 6, 8, 12, 15. After sorting, the intervals remain in the same order. Comparing the start time of the second interval, 6, with the end time of the first interval, 10, we find that 6 is less than 10. This indicates an overlap between these two meetings. As a result, the function immediately returns false, since it is not possible to attend all meetings when any overlap exists. In another scenario, consider the case of a single meeting, such as 10, 20. Here, the input contains only one interval. After sorting, the intervals remain unchanged because there is only one. Since there are no consecutive intervals to compare, it is impossible for any overlaps to exist. In this case, the function directly returns true, as the person can trivially attend all meetings. From these examples, we can observe that sorting the intervals by their start times simplifies the process of detecting overlaps. By ensuring the intervals are in chronological order, we can efficiently check for overlaps using a simple condition. If the start time of an interval is less than the end time of the previous interval, an overlap exists. This approach is both clear and effective. If no overlaps are detected after processing all intervals, it means the person can attend all meetings. The time complexity of this solution is primarily determined by the sorting step, which takes n log n for n intervals. The subsequent loop to check for overlaps runs in n time, resulting in an overall complexity of n log n. The space complexity is 1, as sorting is done in place without requiring additional storage. This solution is efficient and scales well for datasets of varying sizes. By combining sorting with a single pass to detect overlaps, it provides an optimal balance of performance and simplicity, making it a robust choice for solving this problem. To understand the time complexity of this algorithm, we need to break it down into its two main steps. First, we sort the intervals based on their start times. Sorting a list of size n takes O, n log n, time, which is the costliest operation here. Then, we perform a single traversal of the sorted intervals to check for overlaps. This traversal is linear, taking O, n, time. When we combine these two steps, the total time complexity becomes O, n log n, plus O, n. However, since O, n log n, grows faster than O, n, as the input size increases, the overall time complexity simplifies to O, n log n. This holds true across all cases best, average, and worst, because sorting is always required, regardless of whether the intervals are already sorted or have no overlaps. Now, let's analyze the space complexity. Sorting the intervals is typically done in place in Python, thanks to its timsort implementation, which means it doesn't require additional memory beyond a constant amount. This gives us an auxiliary space complexity of O1. Additionally, the iteration step doesn't require any extra space either, as it simply processes the input list without creating new data structures. While the input list itself occupies O(n) space, this is not considered auxiliary space since it is part of the problem's input. Therefore, the overall space complexity for this algorithm is O1, making it very efficient in terms of memory usage. Let's compare this optimized approach to a brute force solution. A naive method would involve comparing every pair of intervals to check for overlaps. With n intervals, there are n1/2 pairs to evaluate, resulting in a time complexity of O(n superscript 2). This is significantly less efficient than the optimized approach, which reduces comparisons by sorting the intervals first, achieving O(n log n) time complexity. In terms of space, the brute force method still has an auxiliary space complexity of O1, the same as the optimized approach. However, the time savings in the optimized solution make it far more practical for larger inputs. Finally, let's clarify why the time complexity of this algorithm is O(n log n). The sorting step is the most computationally expensive part, as sorting a list of size n using Python's timsort requires O(n log n) operations. After sorting, the iteration step only takes O(n) time, which is asymptotically smaller and does not affect the overall complexity. Therefore, the sorting step dominates, and the final time complexity is O(n log n). As for space, because sorting is performed in place and no additional data structures are used, the auxiliary space complexity remains O1, making this both a time and space-efficient solution. A common issue when solving interval-based problems is forgetting to sort the intervals. Most algorithms require intervals to be sorted by their start time, or sometimes their end time, to ensure correctness. Without sorting, you might process intervals in an order that misses critical overlaps, particularly between intervals that are not adjacent. For example, imagine trying to check for overlaps in unsorted intervals. You could easily skip overlaps between distant intervals. Another frequent mistake is misinterpreting the condition for overlap. It's important to remember that two intervals overlap if one starts before the other ends, and vice versa. The proper condition is checking if interval 1's end is greater than interval 2's start, and interval 2's end is greater than interval 1's start. Using conditions like greater than or equal to could lead to false positives, especially when intervals just touch but don't actually overlap. These errors can lead to subtle bugs, so being precise with both sorting and overlap conditions is critical in implementation. Inefficient nested loops are another pitfall when solving these problems. A brute force approach, which compares every pair of intervals, has a time complexity of O(n squared). While this might work for small datasets, it quickly becomes unfeasible as the number of intervals increases. For example, with n greater than 10,000, this approach will likely time out. A far better approach is to sort the intervals and use a single traversal, often paired with a data structure like a min-heap, to reduce the complexity significantly. Additionally, edge cases can often trip up solutions. For instance, intervals with zero length, such as 5, 5, or inputs containing just a single interval are easy to overlook, leading to off-by-one errors or incorrect results. To avoid this, make it a habit to explicitly account for such cases during coding and testing. Finally, some problems might include intervals with negative values or very large ranges. If your code doesn't handle these scenarios, it could result in overflow errors or incorrect behavior, so always verify the constraints and design your solution accordingly. In interviews, it's important to focus on key problem-solving strategies for interval-related challenges. Sorting is often the first and most crucial step. It simplifies the problem and sets up your solution for success. Make sure to mention this during the interview to demonstrate clarity of thought. When dealing with overlapping intervals, efficient data structures like min-heaps or algorithms like the sweepline approach are excellent tools to discuss. They not only optimize performance but also show your familiarity with advanced techniques. Another way to stand out is by proactively discussing edge cases. For example, bring up scenarios like empty inputs, zero-length intervals, or intervals with extreme values. This shows the interviewer that you think critically and test thoroughly. Finally, recognize common patterns in interval problems, such as merging, finding overlaps, or counting active intervals. Identifying these patterns allows you to quickly choose the right approach, which is a skill interviewers highly value. To deepen your understanding of interval problems, it's helpful to explore related challenges that build on similar concepts. For example, in meeting rooms 2, the goal is to find the minimum number of meeting rooms needed for a set of intervals. This problem expands on the basics of detecting overlaps and requires efficient management of active intervals. Another classic problem is merge intervals, where you combine all overlapping intervals into one. It's a great example of how sorting and careful traversal can simplify a seemingly complex task. Non-overlapping intervals takes a different angle, asking you to remove the minimum number of intervals to make the rest non-overlapping. This requires a strategic approach to minimize removals while maintaining the sequence. Finally, the insert interval problem challenges you to insert a new interval into a sorted list and merge overlaps as needed. These problems not only reinforce interval concepts but also introduce variations that can prepare you for a wide range of challenges. There are several alternative approaches to solving interval problems, each with its own strengths and trade-offs. The sweepline algorithm is a powerful technique that treats the start and end points of intervals as events. By sorting these events and using a counter to track active intervals, you can efficiently solve problems that involve counting overlaps. This method has a time complexity of O(n) log n due to sorting, followed by O(n) for traversal, making it highly efficient for large datasets. Another approach is to use a min-heap. After sorting the intervals, you can use the heap to track the n times of overlapping intervals, pushing new intervals into the heap and removing those that no longer overlap. This method simplifies managing overlaps but requires additional space for the heap. While both of these approaches are efficient, brute force remains the simplest to implement. However, its O(n)² complexity makes it impractical for large inputs. Each approach has its place, and understanding their trade-offs can help you decide which one to use based on the problem constraints and dataset size. Thanks for joining me in solving the meeting rooms problem. We reviewed the brute force approach and highlighted key takeaways for handling interval scheduling challenges. Don't forget to practice similar problems and subscribe for more coding tips. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!